All right, continuing with the next piece where we have a function in age and height, so simulating kind of a previous example. Is this a function? Is it a one-to-one? So here, remember, if it's a function, that means that every input value is unique. And so notice here I have two 5s, so that means that 5 goes to 42 and 40 and 42, and that can't happen. One x value can only go to one y value for it to be a function. So, whoops. So this is not a function, excuse me. And so then the question whether it's one-to-one doesn't even exist. We don't even need that question because if it's not a function, it cannot be one-to-one. Okay? Now, for example, let's look at this scenario. Is it a function? Is it one-to-one? If each percentage earned translates to one letter grade, would this be a function? Is it one-to-one? So this, without giving any numbers, could or couldn't be possibly. So if I say I have 82%, that translates to a B. If I had a test grade, say it's on test, of a 91%, that translates to an A. If I end up having 86%, and that translates again to a B, and at this point, if I say, those are my 3 tests for the semester, and do I have a function? Well, do all of my inputs that are existing, are they unique, would be the question. In this case, yes it is. Doesn't matter whether these are the same, that's okay. It's that for a function, these have to be different. Now in a case that, so we're going to kind of go off the assumption that these were our numbers. In the case that maybe I had a 4th test and I ended up getting another 91%, which translates to an A, that would not be a function in that case, okay? So I'm going to kind of put an X through that because we're just going to kind of look at these numbers. And in this case, if I were to use those 3 tests, would that be one-to-one? And in one-to-oneness, we're looking at also not only going the forward direction for it to be a function, but also the backwards direction to where each of the outputs must be unique as well. And because of these 2 B's, therefore, it is not one-to-one. Okay? Now, that's by looking at tables. What happens if we're given graphs? If we're given graphs, that means that we can use 2 different tests in order to determine if a graph is a function. And therefore, they're called the vertical line test and the horizontal line test. Now, a graph is a function if, when any vertical line is drawn through that graph, the line intersects the graph in only one point. Therefore, also going the other direction of one-to-oneness, we can use the horizontal line test as well for that. A graph of a function, so remember it has to be a function, you must check that first, is one-to-one if any horizontal line crosses the graph in exactly one point. Now for you visual learners out here, you will love this because we want to look at vertical lines and horizontal lines to determine. So it can only intersect my vertical line that I draw in one point, or cross the blue graph. Okay, so if I start drawing vertical lines on this cubic that I have a graph, I intersect it here, 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 and each time on each line I have only one point. Therefore, yes, it is a function. Now, if I then turn my attention to is it one-to-one, that means I need to draw horizontal lines. Now, if I draw these 2 and stop, I intersect in one spot. So you might think it's a yes, but what happens if I go right through the middle? I have 1, 2, 3 intersections there. Therefore, no, that is not a one-to-one function. Okay? All right. Now, the next thing that I have to do is a line. A line or a linear relationship ends up, is it a function? Is it one-to-one? Well, let's try for a function. Means we want to look at all those vertical lines that are going through there. And therefore, intersecting in one spot gives me, yes, it is a function. If I look at the horizontal lines now, as I come across here, I'm getting kind of marked up here, but looking at the green and the blue, I only have 1, 2, 4. Each time I end up having only 1 point. Therefore, yes, that is a one-to-one function. Okay. All right, and our last example here that we have for the, kind of looks like a circle, but really I would call it an ellipse. If I try for a function and I draw this line right here, notice I have 2 points that cross, therefore automatically, no, that is not a function. And is it one-to-one? Well, because I marked no on the first one, I don't even have to answer that second one. Okay. All right, let's move to the next one. Move to the next one. All right, so we're going to look at two different things here when solving and evaluating functions. That's basically kind of two things that we do when we're looking at functions. One is going forward in a sense, and the other is going backwards. So typically we either evaluate or solve a function. Evaluating a function is what we do when we know an input value. Then we use that and the function to determine the corresponding output value. Evaluating will always produce just one answer, one result, since each x value or input corresponds to exactly one y value or an output. Now, when solving the function, one is given the output, and we must find the input. And in this case, when you're solving for a function, there could be more than one solution. So if you think of that cubic on the previous page, when we were trying to look at, is it one-to-one, and I intersected that graph in 3 different spots, this could be 3 different solutions right there, in a sense, when I'm solving that function. So let's try this 3 different ways. Let's try this with our table. Let's try it with our graph. And then we're going to kind of get into some functions. So look at the table. Notation says I need to evaluate g of 5. G of 5, here is my function notation. Q is the output. N is the input, or the x's and y's, pretty much. The x on the inside, the y on the outside. And g this time is just a name. Remember, don't freak out about that. You can use f's, you can use g's, you can use w's. Whatever letter that you choose, it's just a name. All right, so if we want to evaluate g of 5, basically we're asking if my input is 5, when I ask for g of 5, it's asking for the output q, okay? So if I look for n equaling 5, which is right here, I need to now look at the corresponding y value or the corresponding output. Therefore, g of 5 is equal to 8. Now let's move down below that and ask for the value of g of 4. What is g of 4? G of 4, again, I'm looking for the output or the q value when n equals 4, and it corresponds to 6. Therefore, g of 4 is equal to 6. Now, coming over here to solve, now we're looking for the n value when we're given the output, which is now q. So if I tell you that q is equal to 6, I would come along here and find 6. Now, actually, I see 2 of them. I see 1 here, and I also see 1 here. If there are 2, that means that's one of those situations where we have more than one answer. And so if q is equal to 6, then the n value that made that true was 4, and this one, which is 2. So 4, 2 would be my solution for that equation or that function. Now, try to find out what is g of n. G of n equaling 7, so the q value is 7. We want to find the corresponding n. So I look along my outputs, I find 7, and then I look at its n value, which is 3. Therefore, that would be my answer. Okay? All right, next, let's look at a graph. And in a graph situation, we want to make sure that we can identify what is our input, what is our output, okay? So for the graph of f of x, and I'm going to say equals y, so remember, That is the output value for f of x, that whole thing collectively. Part A is asking us for f of 2. F of 2 means I want the y value when x equals 2. So let's go over here as a reminder for our coordinate plane. Remember, to find these points on this parabola, I move over in the x and up or down on the y. So to go to x equaling 2, I'm going to find the corresponding point, and I'm going to write its ordered pair. So that is the ordered pair 2, 1. The input is 2, the output is 1. Therefore, when x equals 2, the y value is 1. So f of 2 equals 1. Now let's skip down to letter D, because then we also have an evaluate. So let's find when x equals 0. So here's negative 1, 0. Here's the corresponding point. That is the point 0, 1. And again, if x equals 0, what is the y value in this case? It is also 1 again. That is the output that goes when x equals 0. Okay? Now, doing it differently, going and solving this equation, now I'm looking at, and you can exchange that f of x for y. I want to know when y equals 4, what is the x value? So if y equals 4, where is 4 on the y-axis? It's right here. So along this line, I'm looking for points on the blue graph. 1 is here, and 1 is here. Now, that's when y equals 4. So I need to determine what is the x value at this point, which is negative 1. What is the x value at this point, which is positive 3. Therefore, the solution that I have here is negative 1 and 3. Now, if you were to write 3 comma negative 1, that would work as well. You don't have to have them in a specific order. All right, let's check out when y is equal to 0, if you want to write that as y equals 0. So where is y equaling 0 along here? Well, y equaling 0 is here. And along, where is it across the blue? It is this point right here. And what is the x value when y equals 0? It corresponds to that piece right there, which is 1. So a lot of 1s going on there. Some of those are x values, some of those are y values. Make sure that you can keep those straight. All right, next. What happens if I give you formulas? Now we go into the idea where I give you a mathematical rule, and I need to figure out some of these function values. But first, sometimes it's convenient to solve equations or formulas, however you want to look at it, for certain variables. And in this case, we're practicing here to express this relationship as a function where p is equal to f of n. Basically, it's asking me to get p by itself, and what's left over on this side is going to have an n in it. That's really what we're looking at, okay? So I hope you remember how to do some two-step equations, because this is kind of what that is. If I want to get this term where p is by itself, I'm going to have to first get rid of this 2n. Now, that's a positive 2n, so to get rid of it to the other side, I have to do the opposite, which is subtract 2n and subtract 2n. This goes away, leaving me with 6p on the left side. Bring your equals straight down. Now you can write that as 12 minus 2n or minus 2n plus 12. I normally get the variable in the front, so we end up having that. Then to find my final answer, to do the undo of this product, I have to divide by the number next to the letter, and therefore p is by itself. So this cancels out and leaves me a 1. There's an invisible 1 right here. I can reduce this fraction as a negative 1/3. I can't do anything else more than that. Times n, or you could have like negative n over 3. That would be a valid answer. And then dividing these two, 12 divided by 6 does give me a positive 2. So that would be my final answer for this one, when I'm looking at solving for a certain variable given a formula. All right. Now we're moving into that formula, okay? So I need to find f of negative 3. F of negative 3, I'm letting you know that x is equal to negative 3. Therefore, given this rule, it tells me to take negative 2 times every x value and add 3 to it. So I'm, in a sense, going to plug that into the x and evaluate. So I'm going to take -2 and multiply by -3. Again, take out the x, put in your number, and then it tells me to add 3. And at this point, now it's order of operations. I have to multiply first, then add. So if you need to review PEMDAS or GEMA, or please excuse my dear Aunt Sally, please do so. Multiplying -2 times -3 is a positive 6. Add 3 also does now give me 9. Therefore, f of -3 equals 9. Let's try the next one. The next one, I have a function value of h in terms of p. So h is a function of p. The rule says to square p and then add the double of p. Well, notice inside here, that is a p. I can get that from right there, okay? They're telling me p equals 4. So I need to take 4, and I need to put that wherever I see a p in my function. And so I have 2 places to do that. So h of 4 is equal to, I need to put 4 in there and square it, and then add twice of that times 4, and that ends up getting me what I need to operate in order to find my answer. So in order to do order of operations PEMDAS style, that would be you have to square the exponent first and then multiply and then add. So 4 squared, as a reminder, is 4 times 4 with exponents. You don't multiply 4 times 2. But you multiply this number by itself that many times. So 4 times 4 is 16. Then we need to multiply that 2 times 4, which gives me an 8. And our final operation is to add those 2 together, which gives me a 24. Therefore, h of 4 equals 24. And these are examples in which we get numbers as our answers, and not always will that be the case. Okay? So the next one in our notes is g of m is equal to the square root of m minus 4. So that means I need to input that, or 14, because that's what we're looking for. You need to input that in for m. Therefore, g of 14 is equal to the square root of 14 minus 4. Now remember, the square root is the opposite of squaring something. So if I had 16 over here as my 4 squared, when I take the square root of 16, remember we're asking what number did we multiply by itself to get 16, and that answer would be 4. Now, that square root is also acting as like a grouping symbol, so we want to do what's inside there first, which is the subtraction, and get our number, which is 10, and we have the square root of 10. Now, unfortunately, that doesn't have a nice perfect square, as we say, because the number that we multiply by itself to get 10 is very nasty, okay? So your answer could be left in this exact form of the square root of 10. In our final example here for this page, we have g of x is equal to 5x minus 2, and basically we're just going to operate with 2 individual functions. So I want to operate and find g of 10 and what g of negative 1 is and subtract the 2. So looking at g of 10, that means I'm going to put 10 in for x, so that means I take 5 times our 10 and then minus 2, so I'm going to kind of put those in brackets to represent that that's one quantity as our g of 10, minus, then I'm going to put negative 1 in for x. And so I'm going to take 5 times a negative 1 and then subtract 2 also. And therefore, I now need to just work with, excuse me, I don't know why this is doing that. We are going to be able to do order of operations and solve for that. So multiply first, then subtract. So I get 50 here minus 2 actually gives me a 48 that I need to subtract, with 5 times negative 1 gives me a negative 5. When I subtract 2, that ends up being a negative 7. If you need to use your scientific to check yourself out, please do so. And so then I end up having these double negatives, which if I do a negative times a negative, that becomes a positive. And 48 plus 7 now gives me 55. And that would be my final answer for that. Okay? So, evaluating functions, we do that quite often. Make sure you are able to do that. Now, we're going to have two last ones here before we actually do a solve of a function. And these two last ones are actually going to end up being in terms of a variable. So not all the time will you end up landing or ending with just a number. Now notice here my function is 3 times some number add 1. What I'm looking for now is f of m. So remember that m is my x value. I'm going to replace that x, so take that out if you have to, and put the m in. So f of m looks like this, 3m plus 1. That's it. I don't have an exact number, so I can't take that number times 3 and add 1. The best I can write it is 3m plus 1. But notice I have this 2 hanging out up front. Now that 2 does not have anything between each one of those. It does represent to multiply. If I put a 2 out in front like that, it's not doing what I need it to. I need to do 2 times the whole thing. And in order for me to multiply 2 times the whole thing, I need to include parentheses there, which then engages the distributive property where I have to take 2 and multiply it by 3m and 2 times 1. So 2 times 3m, make sure you multiply just the numbers out front, so that gives me a 6m. And 2 times a positive 1 gives me a positive 2, and that would be my final answer. Likewise, over here, I'm now looking for f of m minus 2 with that same function. So that means wherever I see my x, I have to put this whole quantity in. Now again, I need 3, and then I have an m minus 2, but I don't want to just write it like that because I need 3 times the whole thing. So that means I need to engage my parentheses there, and then we can't forget about our plus 1 in our formula. So 3 times what's inside of my function and add 1. Now again, this is another distributive property that I have. So I'm going to multiply 3 times m, which gives me 3m. And 3 times a negative 2 gives me a negative 6. Add 1, don't forget that. And then it's about of like terms, combining. So we want to combine like terms, which in this case there is no other m. I just need to combine my numbers here. So negative 6 plus 1 gives me a negative 5. So I'm going to rewrite 3m and then do my minus 5. So again, my answer is in terms of a variable, and that's a-okay. You do not have to worry about ensuring that every answer you get is a number. All right, last one on functions to be able to, in this case, solve, and then we're going to get into some basic graphs. We sometimes call them parent graphs in math. And so here, I'm given g of x is equal to negative 4x plus 5, and I need to solve for when that g of x is equal to 25. So this is kind of the output. I'm telling you, that's the output, which has to come from this output as well. So notice, I needed to just basically do a substitution. If g of x equals 25, I can put 25 right in here and solve that equation. Now, whether I write it as 25 equals negative 4x plus 5, or I write it in the reverse sense, negative 4x plus 5 equals 25, I don't care which way that you like it. You can solve whichever that you wish, okay? I like to have the variable on the left, so I'm going to solve using the left, or this bottom one. And in order to get x by itself, don't forget we got to get rid of this plus 5 first. So let's subtract 5 from both sides. Draw the line if you have to. I can bring down negative 4x. Those two things cancel. And 25 minus 5 is 20. Now, how do I undo this? Well, that's a times. So to undo a times, I must do the opposite, which is divide by the number next to the letter. Therefore, my negative 4's cancel out, leaving me with x on the left. And now I need to do that 20 divided by negative 4, which is a negative 5. So 20 divided by 4 is 5. Positive divided by a negative is a negative. And that would be our final answer. Okay? All right, graphing with basic functions. Now, before we go over some basic functions we will use in this course, then we need to make the connection between ordered pairs and function notation. So this is very, we kind of sort of, in a sense, looked at it, but not really of this form. If I have the ordered pair, remember that ordered pair is some x comma y. Remember, our function notation is of the form f of x equals y. So we're just looking at it in two different ways. So if I say 2, 5 is my point, in function notation, there's going to be my 2, there's going to be my 5. So it would equate to f of 2 equals 5. And that is the function notation. If I say negative 1, 8, that's my ordered pair. What does it look like in function notation? Again, here's my x, here's my y, my negative 1 and 8. F of negative 1 equals 8 would be what I would write for function notation. Okay? All right. Now, like I said, at this point, we're just going to try to recognize these graphs. We're not going to start shifting and moving them around because that is to come. So let's start with the most basic, which is a constant. And so it is of the form f of x equals c, where c is some number. Now, for this position, I could say I'm going to take out the 2 and I'm going to make that c. Let's say that that's c. Now, no matter what x values that I put in there, so I could say x, y, if I wanted to put negative 1, 0, and 1. No matter what x values that I put into that function, that same value is just c, c, c. So, our y value stays the same. Where's the y value of c? It's right here. If I were to plot all these points, negative 1c, 0c, 1c, notice what kind of line is forming there. That gives me a horizontal constant line. Okay? If I look at the identity function, f of x is equal to x. This is also referred to as the linear function. We could do a t-table for that if you want as well. Basically, if I throw negative 1 in, 0 and 1, let's say. If I throw negative 1 in for x, I'm going to kick out negative 1. If I throw 0 in for x, I get 0. So you notice you're getting kicked back the same exact value. So at negative 1, I'm here. 0, 0, we're here. And 1, 1, we are here. Therefore, if I connect that, that ends up giving me a line basically that bisects the first and the third quadrant. So this would represent our linear function, the identity of that. Absolute value, we have straight up and down lines for the absolute value of x. And as a reminder, absolute value means the distance from 0, and we should know that a distance is never negative. So therefore, if I look at, say, negative 2, negative 1, 0, 1, and 2 on a t-chart for this, let's start with 0. If I put 0 in there, the absolute value of 0 is 0. That's the distance from 0, nothing. If I put 1 in there, the distance from 0 to 1 is 1. If I put 2 in there, the absolute value of 2 is 2. Now, when I throw my negatives in there, if I put negative 1 in there, the distance between 0 and negative 1 is 1. It's not a negative 1. Okay, we don't talk about we're walking negative 5 miles. It does become positive. So if I throw negative 2 in there, then our output for the absolute value is 2. Now when plotting these points at negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2, I get a V shape that is forming. And in order to try to make that straighter than what I just did, in order to graph that, we can connect those. We can connect those, and we have a V-shaped graph for my absolute value. Okay? Again, later on, we're going to be moving these things side to side, up and down, and such. Okay? All right, let's look at our quadratic. The quad kind of is deceptive in the name here. This function looks like f of x equals x to the second power. You would think it might be a 4, but it actually is a second power. If I end up throwing in some of these values, like negative 2, negative 1, 0, 1, and 2, the rule now tells me to square each number. So negative 2 squared is the same as negative 2 times negative 2, which is 4. Negative 1 squared is the same as negative 1 times negative 1, which is 1. 0 squared is 0. 1 times 1 is 1, and 2 times 2 is 4. Now we can graph these points, negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Now, this almost kind of looks like a V, but if we actually get into some of those values between 0 and 1, you actually get kind of a U shape there. And so it is a symmetric graph, meaning I can split it over the y-axis, and the same is on the right as it is on the left. Okay? All right. We're halfway there almost. The square root, f of x is equal to the square root of x. We saw a square root earlier, reminding you that that is the inverse or the opposite of our squaring. And so if I do a t-table, we're looking for nice values to be able to graph. Now, if I put 0 in there, we do -2, -1, 0, 1, and 2. Let's just start with 0. The square root of 0, what times itself is 0, and that's 0. What times itself gives me 1? Well, that is 1. Now, if I put 2 in there, is there a number that's nice that I can multiply by itself to get 2? And the answer is no. Okay? Now, if I choose 4, what number by itself multiplies to give me 4? That answer is 2. So I have these nice points here, 0, 0, 1, 1, 4, 2, and I get those 3 points. Now, let's talk about negative. If I throw a negative underneath there and I get, what is the square root of -1? You might think to say 1, but remember, 1 times 1 has to be itself is a positive 1, not a -1. So remember, in order to get a negative answer, I have to have one sign that's different than the other. Therefore, there is no square root with -1 in the real numbers. Therefore, there's not going to be any answers here. This is going to be my graph. So it's kind of like half of my parabola over here turned on its side. Okay? All right. F of x is equal to x cubed. And so if we do a t-chart with that, and in any case, when you're graphing, you can always do a t-chart. But I want you to get away from that and kind of know these functions. And so be familiar with them so we can sketch them pretty easily. So -2 cubed is what I need to do. Take -2 and throw it into my function. So -2 times -2 times -2 is -8. -1 times -1 times -1 is -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. And 2 times 2 times 2 is 8. So if I'm going to graph those 5 points, go to -2, -8, which is about right there possibly. -1, -1, 0, 0, 1, 1, and 2, 8 we could say is about there, way up there, okay? Now, if I were to connect those, I have something that looks like that. And I call that, for lack of better terms, a squiggle. That x cubed is that squiggle graph. Sorry, there's a little bit of a delay.
I'm not sure I understand.
And my watch is going off. All right, and so that would be our cubic. Okay, if we had a smaller graph, actually one that was more precise in there, then that wouldn't be so big on our graph. All right, and our last 3 graphs that we have to go over out of section 1.1 is this. So our cube root is going to be basically kind of an inverse or a reverse of our x cubed. So what we had in our t-chart on the x cubed is going to be reversed on a cube root. So what multiplied by itself, if I throw 8 in there, what multiplied by itself 3 times, and that's a little 3 out front, gives me a 2. Cube root of 1 is 1. Cube root of 0 is 0. Cube root of -1 is -1. And cube root of 8 is -2. So graphing each one of those, going out to 8, 2 could be maybe right there. 1, 1, 0, 0, -1, -1. And -8, 2 is going to be kind of beyond here. So we'll just put a dot right here. So what's going to happen is it's going to be that squiggle still, but it's going to be turned on its side. So that is your cube root function. Again, be conscious of what it looks like. Be conscious of being able to find its points and recognize what it looks like. Second to the last one is the reciprocal. we have f of x is equal to 1 over x. And if I were to plot some points, I'm going to do it up here because I kind of run out of room next to that graph on the left. And I try to do some of these points. Now I'm going to kind of strategically start with -2, -1, then I'm going to throw in -1/2, 0, 1, half, 1, and 2. So if we plug in each one of those values into my reciprocal, plugging in -2, 1 over -2 is -1/2. Plug in -1, 1 over -1 is -1. Plug in -1/2. Now, when you talk about a reciprocal, if I say 2/3 is my fraction, to do a reciprocal, we basically flip the fraction, okay? It is 1 divided by that. You're actually dividing by 1 divided by 2/3 to get 3/2, which means that you flip and multiply on that second fraction. So, when I throw -1/2 in here, what I get is -2. Again, you can check that on your scientific calculator if that makes you feel more comfortable. When I throw 0 in, I get 1 over 0. Undefined. Remember, you can never divide by 0. That is an undefined operation. Okay? So in our graph, what that symbolizes by is what we call an asymptote. So it's going to be a dashed line here when y equal, or when x equals 0, excuse me. When I throw in 1/2, again, if that reciprocal means I flip it, so I flip it over and get a 2. 1 over 1 flip gives me a 1 again, or plug in 1. 1 over 1 is 1, and plug in 2. 1 over 2 is 1/2. And so, looking at plotting these points, starting at 1/2 to 2, we would end up 1/2, 2 gives me this point. 1, 1 is that point. And 1/2, or 2, 1/2 would give me that point. So I end up having a graph that looks something like that in the first quadrant. And if I then take in these negatives here, -2, -1/2 is about here. -1, -1. And -1/2, -2 would be here. So it kind of looks the same except for it's in the third quadrant now. And that is what we refer to as the reciprocal graph. Okay. And our last function, finally out of section 1, they seem to always cram in so much information into a first section. We have the reciprocal squared is 1 over x squared as our function. Now, if you do a t-table on that, if I throw in 1/2, square it, we get 1/4, flip it, gives me a 4. If I throw in 1, 1 squared is 1, 1 over 1 is 1. If I throw in 2, 1 over 2 squared, so 2 squared is 4, so a 1/4, I end up getting pretty much the same thing. Okay, now they are different because the points wouldn't be exactly the same as what we have over here with this reciprocal function. Okay, now when I square something, remember we talked about that being always positive. So if I take -1/2 and I multiply it by itself, I square it, I get a positive 1/4. When I flip it, that gives me a positive 4. If I do -1 in there squared, it gives me a positive 1, and I get 1 over 1, which is 1. And then I put 2 in there, say -2, excuse me. -2 squared is 4. 1 over 4 gives me a 1/4. So this is a mirror image, basically, of what we had in the first quadrant. And when I taught high school, my high school kids, we talked about that being what we called the Atari function, because if you ever played an Atari, that kind of looks like the symbol for that. All right, so again, at this point, you just need to start learning what the names are and be able to identify points on that graph and a t-table and be able to choose those things. So we're not getting too involved just yet with these, but we will later on. So start becoming familiar with these basic graphs. All right, very well. I will see you in section 2.